So far we performed both RG and flux calculation for shell model, which I did it in full detail. So, that was simple, so it could be done, but Navier-Stokes equation is bit more complicated, and but I will show you how to proceed. I will not exactly show you all the details, but you will get an idea. Okay, so, this is the Navier-Stokes equation. Just to recap, this U is the velocity field, nonlinear term, and as before lambda is equal to 1 and that is unchanged under Rg. So, we do not worry about it, we only renormalize the viscosity. And this external force, we assume the external force is active at large scale. Okay, we need this because we are assuming steady state, otherwise my energy spectrum will decay with time, which is not which will make it more complicated. Okay. So, you want the spectrum to be fixed. So, I can do ensemble average or okay. So, we need that forcing, but that is at large scale. So, for the inertial range calculations I will not have FU. So, that will not complicate my life in this scheme, and so I must say that the scheme I am following is by Zhou and his co-workers and Mecom. So, these are the two groups which propagated this VFRG. There are other RG schemes. I'll do one more, maybe not today, but I'll not do RG full, but I'll show you how it is done by genetic function. Okay, which is you can easily see that is more complicated, but I am following this people's scheme. Okay, and grad P will add something to u dot grad u, but for my calculation I will say that okay, I will ignore that term. Okay, I am not ignoring it, but I am hiding it. If I ignore it, then I will get Burger's equation, which is a very different physics, but I am hiding it to simplify my algebra, and we assume incompressibility. So, this theory will not work for compressible Navier-Stokes. So, in Fourier space we will work in Fourier space. So, this is Wilson RG, we are motivated by that. So, that equation in Fourier space is this. So, viscous term has come to the left, this is nu k squared, and this is the kinematic viscosity, the original viscosity, and this is the pressure term, and the nonlinear term has become a convolution, right, k dot u q u p, and this is the integral. For shell model we did not have the integral, we had just 3 terms, but now I had to work with the integral, which makes life bit complicated, and this is the force Fu, which is active only at large scales. Okay. So, we again go back to our RG procedure. So, imagine that I am in the inertial range, okay, I am in the inertial range, and I am here at this shell. Now, my shells are, I do it by hand. For shell model they are all single variable for every kn, but now I have many variables, but as before kn plus 1 by kn is B. Okay, but there are modes sitting in between. Okay, or there in fact the 3D or 2D, we will focus on 3D. So, there are many modes in between magnitudes. So, it is a 3D. So, there are in fact a full lot of modes in this shell, and the inner radius is kn, outer radius is kn plus 1. So, there are k squared times the distance between the shells. Okay. So, we denote that by k greater symbol. So, this is to be coarse grained. After this operation I am going to average out and basically see the effect of this coarse graining on viscosity. Idea is exactly the same as before, except we have more calculations. Okay. So, this is the mode, these are the modes which I am going to coarse grain, that means I am going to average and they will not appear in the renormalized equation. Okay. So, as before I am going to this nonlinear term. So, if you look at the filter, I look at any in the less region, this is to be retained, right. These modes R to be retained. So, when I look at any velocity mode in this regime, so this will be less, this will be less, okay. Pressure also will be less, but the nonlinear, well, pressure I will just keep quiet right now, but here there are product of U's. So, what are the possibilities? Two U's are in the left of Kn less, but there are possibilities that both U's are greater, or one U is less, the other U is greater, or this is greater, this is less. There are 4 possibilities, right. So, it is a convolution. So, this integral will involve all combination of U's, less greater, greater greater, less less. Okay. So, my equation, if I divide in this part, I will have less less. I said I am hiding pressure now, so I am not going to keep that. Then there are 3 more terms. Now, if you look at this part of the equation, other than pressure gradient, it looks same as before. Okay. These are annoyance, right. These are something, well, I got some new term, what to do with that. So, I need to model these terms A, B, C, I need to model them. Okay. Now, if I do simple model, let us do a simple model. Okay. So, if I average them, coarse grain means I average the U grade modes. So, simple thing is, well, I am going to write this as, in fact, similar shell model, I write this U less, this is not to be averaged. So, I am saying that they are not quite connected very strongly. So, I am going to write this U greater of P. And what is this? This should be 0, because I assume it to be randomly fluctuating field. U is random, there is no mean. So, this is 0. So, these 2 terms go away, and we are left with this term, out of 3 only one term, greater greater, and I need to compute this greater greater term and see whether there it is a non-zero value. Okay. So, what do I do? So, I follow very similar scheme, I do to first order. So, I am going to write the Feynman diagrams. So, what is the prefactor? Minus I k dot, well, I will just write as k, okay, prefactor, and 2 U's, 2 U's. This is U q and this is U p, okay, greater. If I do average here, since P is not equal to Q, I will get 0. So, I go to the next order. How do I go to the next order? Put minus I k. So, let me just the 2 possibilities, expand using Green's function to each of them, but one at a time. So, let us expand this as Green's function, and this is U greater of Q. Now, they will give you 2 U's, correct. Now, what is the condition here at this point? P plus Q must be equal to K, that is the condition for convolution, right. This is G of P, but what is the condition here? So, I had 2 Fourier modes R and S, R plus S must be equal to P, right. Now, of course, I need to integrate over all P's, but I am looking at one P and one Q. Now, if I want to, well, if I want to get a non-zero value, then I need to get them to come together and give non-zero values. So, this will be U of R greater, and what should be condition on R and Q? Imagine that, well, not imagine, you know that U is a real field. So, U of R must be complex conjugate of U star of Q, right. I need that to give you non-zero values. But for real field, U star of Q is U of minus Q. I am not proving it here, but for real fields, this is a property for any real field f of q equal to f star of minus q. This property of Fourier transform for real f. Okay. So, I put a complex conjugate here, I do that. Okay. So, that means R must be equal to minus q, correct. Is that clear to everyone? Now, look at this condition. So, R is minus q, I am just rewriting it here, plus S equal to P. What should be S? Implies S equal to P plus Q. And what is P plus Q? K. So, this must be K. So, this is U of K. Great, no? Why is it great? Because this calculation is giving you a term proportional to U of K, and that I am going to bring it to the left, and that is going to correct the viscosity. Okay. So, this is what happens under this field theory. When I do this one loop diagram or with this perturbation, I get a term which is proportional to U of K. Okay. So, this is what we get. The second term is also similar, but the Green's function is above and correlation function, this is a correlation function. No? So, this Green's function, correlation function, and this is U of K. So, these two, so in fact, we had very similar thing, two loop diagrams for shell model, and idea is exactly the same. So, these loop diagram and this loop diagram will correct the viscosity. Of course, this is in the right hand side. When I bring it to the left hand side, I need to put a minus sign. Clear? So, let's write this stuff. So, I have in the nu bar k squared u less of k. From the right hand side, I bring this to the left. So, I get two Feynman diagrams, this one plus this diagram, okay, and both of them are proportional to u less of k. But if you look at this equation now, so I am going to go back. So, this term is gone and this term I bring it to the left. Okay. So, what does the equation look like after bringing it to the left? So, let us write that d by dt of u of k less plus these guys, right, equal to right hand side is what? Minus I k dot u q q p integral less. Okay. So, now this will look exactly same as the original equation if I can connect these two to that, right. This looks like exactly same equation, but my viscosity has to be modified. So, I write that nu n at the nth step k n squared is nu bar k squared plus these two diagrams. Okay. Now, these two diagrams are to be computed. So, what does the two diagram, what do the two diagram look like? So, this is, let us look at one of them, dp integral. I have Green's function which is p of t minus t prime, there will be integral dt prime, correlation function of q t minus t prime, okay, that is what we will get. There is another term with p q interchange. So, this will be dp, and by the way there are two k's, so k squared will come in front, okay, I can also tell you that one, this k squared will come in front. So, this Green's function is exponential minus nu p p square nu p p squared t minus t prime. That is a model, I assume this form. In correlation function, I write as c of q exponential minus nu q q squared t minus t prime. Okay. Now, of course, this u of t prime, okay, because this is u of t prime at a k, where number k less, but then we use the same Markovian approximation to convert t prime to t. what do I say? Why do I say that? These prefactors are large. So, the integral is basically coming from t prime near t, that is the argument for Markovian approximation. So, this is replaced by u k of t, okay, that is what I want, this u of k of t, right, this is a time t. So, that is Markovian approximation and I need to integrate this. So, I get k squared integral dp c of q divided by nu p p squared plus nu q q squared, and this is my nu n plus 1 nu n times k squared plus nu bar k squared. Okay. So, k squared cancels and I need to solve this integral, but nu bar is small. Okay. So, we get rid of this. Renormalized viscosity is big because it grows with the small k. When I decrease k, it grows more and more. Now, how do I solve this problem? Because C is I do not know what is C, what is nu, but then I go back to again self consistent idea of Macomb and Zhou. So, we write this C as Kolmogorov constant epsilon 2/3 q minus 5/3. Well, this is a modal energy, so I divide by 4 pi q squared. Okay. This detail I am hiding right now, and the viscous term nu p p squared exactly like what I did before, nu star square root of k Kolmogorov epsilon 1/3 p 2/3. Plug this in, I get integral of. So, basically now I get Kolmogorov constant will in fact cancel, one Kolmogorov constant square root comes here, one square root comes here, Kolmogorov constant epsilon cancels, everything basically gets cancelled and you get some function of a constant integral. But the integral is not trivial, this integral involves some change of variables and some massaging, but by doing this algebra I get nu star, I can compute it by if I do the integral properly. Okay. If you are interested, I can share some notes or share a paper which has these details. This is a nice book by Leslie, or you can look at my archive paper. I have a paper on this one in archive 2005. Okay. So, that has this formula for integral. I hope to write a paper on a newer scheme. So, if I do all this stuff, then I get nu star and it is absolutely 0.4. Okay. So, lot of detailed algebra, I get 0.4, which is similar to what I get for shell model. So, this is amazing, no, that this field theory of different models are giving a pretty much correct nu star. Okay. So, this also depends on B, the ratio of k n plus 1 by k n, but we normally take this ratio B as B k n by k n plus 1 around 0.7. Okay. I did this calculation for this and other authors also do around 0.7. So, this is the RG for Navier-Stokes equation. So, we can take a slight break. Okay. So, I hope you got the idea. So, the idea is that we write down the Navier-Stokes equation, we coarse grain, then we get equation where there is a term in the right hand side which does not look like the original equation, but then we solve that, or rather we simplify it using field theory, and the term after simplification looks exactly like this form, which is similar to the viscous term. So, that means this term will correct the viscosity, and then of course, we need to do the integral and make some approximations, and then we get nu star to be 0.4. Okay. This part is so okay. Okay. Now, let us look at so this is the equation I had written before and you plug that in and that will give you nu star in 0.4 to 0.5 regime, and it is possible to compute, it is quite difficult to compute nu star. I told you how to do it for shell model. A similar thing has not been attempted as far as I know for the Navier-Stokes equation. So, one good idea would be to try, well, we did this stuff, but our simulation was only phi 12 cube and that was not really conclusive what should be nu star, but to get nu star from computer simulation. So, we need to compute basically the idea is that look at this u k u star p of t, u of k t, u star of k t prime, this correlation divide by mod u k t mod square average, exactly same as what I did for shell model, and this quantity should be decaying with time. So, that should give us nu k k square t minus t prime, but there are complications. So, it turns out other than this there is a oscillating term. Okay. So, we know that this is oscillating term, okay, omega t minus t prime, and this oscillating term is connected with the sweeping effect, which I will not discuss right now, but these oscillations also come. So, it is a new feature of Navier-Stokes equation, and that complicates this stuff. It is similar thing as what some of you are trying. So, magnetic field will oscillate, right. So, that is what happens here as well, and but only way I believe it can try nu star is computing this correlation functions, and from nu k using RG this model we should be able to get this nu star. Okay. And this needs to be done. Okay. Now, let us go to the next flux calculation.